Here is the exact moment people give up on system design. Someone asks, okay, how much storage does this need? And suddenly there is this wall of numbers on the whiteboard. 100 million users times 2 divided by 86,000 seconds times a million bytes. And your brain just freezes, right? Multiplying huge numbers in your head is genuinely hard for everyone. But the thing is, you are not bad at this. You are just doing it the hard way. Because at high level, capacity estimation is mostly counting zeros and keeping track of your units. You round the numbers and you add up the zeros. That is the heart of it. And by the end of this video, you will do it in your head. And here is what nobody tells you. This math has exactly one job, right? It is not to get a precise correct number. It is to tell you which world you are in. Is this a single mission, a few tens of missions, or a full distributed system? That one answer shapes your whole design. So, let me show you why we bother, then the trick. Then we will size a real system one piece at a time. So, first, why estimate before building? Because the shape of our system depends entirely on its size. Let me give you the clearest example. Imagine a photo app and you casually say, we will keep the photos in our database. Sounds fine, but 2 minutes of rough math says the photos add up to 600 petabytes. A petabyte is a million gigabytes. So, this is a genuinely enormous amount. And here is the right way to read that number. It is not a database cannot hold this many bytes because big databases actually can. It is that photos are large files. You never edit them and you fetch them whole by their name. And that particular pattern is what a different tool, object storage, is built and priced for. So the estimate did not just give you a number, it told you to split your storage. The huge files in object storage, the small searchable details in a database. And you learn that before drawing a single box. And this is the mindset shift. You are not chasing the exact number, right? You are chasing the rough scale. How many zeros? Being off by 2 times is completely fine. Who really cares? One server versus two. But being off by 100 times means you designed the wrong system. And usually, when you estimate, one or two things come out much bigger than everything else. And those are the parts your design has to solve first. That is the quiet gift of estimation. It points straight at your hardest problem. Okay, the core trick. Step 1. Round every number to just one meaningful digit and write it as the digit times a power of 10. So, 86,000 seconds in a day, round it to 100,000, which is 1 times 10 to the 5. And 32 million becomes 3 times 10 to the 7. One friend digit and the zeros. And here is the payoff. The big scary part, the zeros, you handle by simply adding them. Let me just show you. So, you need 30 million times 2 million. You do not multiply that the long way. First, the small front numbers. 3 times 2 is 6. Then, you count the zeros. 30 million has 7. 2 million has 6. So, that is 13 zeros in total. And the answer is a 6 with 13 zeros after it. That's it, no calculator. And to divide, you subtract the zeros instead of adding. So the honest version of the trick is multiply the tiny front numbers and count the zeros. And you might think, is that not cheating, throwing away the real digits? And the beautiful part is no. The inputs were guesses anyway. Let's say 100 million users is not exact. The real number could be 90 or 130 million. So pretending the answer is precise to the last digit is fake accuracy. Rounding is not a shortcut you are getting away with. It is exactly the right amount of precision for the job, right? And to do this fast, you only need a tiny set in your head about four things. First, data sizes. Each step up kilobyte, megabyte, gigabyte, terabyte adds three zeros. A kilobyte is about 1,000 bytes, three zeros. A megabyte, a million, six zeros. A gigabyte, a billion, nine zeros. A terabyte, a trillion, 12 zeros. So KB, MB, GB, TB. 3, 6, 9, 12 zeros. Second, One day is about 100,000 seconds. That is a 1 with 5 zeros. And it is what you divide by to turn per day into per second. Third, a tiny one you will need soon. 8 bits make 1 byte. That matters because network speeds are measured in bits. So to get bytes, you divide by 8. And fourth, the golden rule. Always keep your units written down. Is this bytes or bits? Per day or per second? Honestly, most estimations mistakes are just a lost unit. And notice what is not on that list: the size of a photo or how spiky the traffic is. Those are not facts to memorize because they vary hugely. A photo could be 100 kilobytes or 10 megabytes. Those are assumptions only. You state them clearly at the start and replace them with real measurements later. So let's go do that exactly. Let's size a photo sharing service. And step 0, half the whole skill. Write your assumptions down. Let's say 100 million daily active users, people who open the app that day. And here is the move most people miss. At high level, a photo app is really doing three different jobs with wildly different sizes: people loading their feed, people viewing photos, and people uploading. And we size each one separately. So, our assumptions: each user opens the feed about 10 times a day, views about 100 photos a day, and uploads about 1 photo a day. A photo is about 1 megabyte. And for the busy hour, we will assume the peak is 5 times the average. A photo app has strong evening and event spikes. So 5 is a reasonable stated choice, not a law. Job 1, the feed requests, the app's main traffic. Quick note on wording. For the app, we count requests per second, RPS. Later, the database might see a different number of queries per second, which is a separate thing. So, 100 million users times 10 feed opens each is 1 billion requests per day. Divide by the 100,000 seconds in a day. Count the zeros off, and that is about 10,000 requests a second on average, times 5 for the peak, about 50,000 requests a second. And that is the number that will size our application servers because feed requests actually hit our servers. Hold on to 50,000. Job 2, viewing photos. And this one is completely different. 100 million users times 100 views is 10 billion image loads a day. Divide by the 100,000 seconds, and that is about 100,000 a second on average, and half a million a second at peak. But, and this is the key insight, these do not hit our application servers. A photo is a fixed file, so it is served by a CDN, a content delivery network. Copies of the file kept near users, which only reaches back to our storage when it has to. So, this giant number is a delivery problem, not a server problem. And mixing these two up using photo views to size your servers is the single most common estimation mistake there is. And job 3, uploads. 100 million uploads a day divided by 100,000 seconds is about 1000 a second, 5000 at peak. Small in count, but each one is heavy. It has to be stored, copied, and processed into different sizes. So it drives our storage and our background workers. So already, just by separating them, the architecture is appearing on its own. Feed requests to the server, photo views to a CDN, uploads to storage and workers. Three numbers, three different parts of the system. Now, the big one, storage, and it comes from the uploads. 100 million photos a day times 1 megabyte each. Count the zeros. 8 plus 6 is 14 zeros, and that is 100 terabytes every day. Over a year is 365 days. Round it to 400. 100 terabytes times 400 is 40,000 terabytes, and 1000 terabytes is 1 petabyte. So, about 40 petabytes a year. Over 5 years, about 200 petabytes of actual photos. And if we plan to keep 3 copies for safety, around 600 petabytes. And there is our number from the start, which, as we said, means the photos live in object storage. And only the small details about each photo, who, when, where the file sits, go in a database. And that details table is still huge, around 200 billion rows over 5 years. So a single database machine is unlikely to be enough, right? We would shard it, split it across machines, choosing how to split based on how we look it up. And the delivery side, bandwidth from those photo views. We use the peak, half a million views a second, each about 1 megabyte. That comes to about 500 gigabytes a second flowing out at the busy hour. And to feel that, network links are measured in bits. And a typical 10 gigabit link divided by 8 carries about 1 gigabyte a second. So, 500 gigabytes a second is like 500 of those links running non-stop. Serving that from one place is a hugely expensive delivery problem. And faraway users would be slow, which is exactly why the CDN exists. And here is the number that makes the CDN earn its place. The CDN keeps copies near users and serves most requests itself. Only the ones it does not have reach our origin, our own storage. The share it can serve is the cache hit ratio. For photos, let's assume 95%. So, of that 500 gigabytes a second, the CDN serves 95% at the edge, and only 5%, about 25 gigabytes a second, actually reaches our origin. Now, 25 gigabytes a second is still a serious amount. It does not just vanish, right? But it is 20 times smaller. And now we can size that origin path on its own. One estimate and the whole delivery design has a shape. Okay, back to the feed servers. We said 50,000 requests a second at peak. But how many servers is that? And here is a honest limit you must know. The thing is, you cannot get the server count from request per second alone because how much one server can handle is something you measure, not a number you can look it up in a table. But latency, how long each request takes, helps us here. There is a simple, powerful rule. The number of requests happening at the same time equals how many arrive per second times how long each one stays. So 50,000 a second times about a fifth of a second each is about 10,000 requests in flight at once. And that pressure, 10,000 at the same time, is what a server really feels. Open connections, memory, the state of each request, and the connections onward to other services. That rule has a name, Little's Law. But forget the name, just remember how many arrive times how long they stay. And the final count comes from a load test. You push more and more traffic at one server until it starts to strain. And you find, let's say, one server safely handles 500 requests a second at a good speed. Then it is simple division. 50,000 at peak divided by 500 each is about 100 servers plus some spare for the ones that crash and for growth. So call it about 150. And notice the key thing that 500 came from a measurement, not a formula, right? That is the honest boundary of estimation. It gives you the shape, 100-ish servers, a CDN, object storage, background workers, and real measurement fills in the exact number. And here is the move that shows you truly understand this. Take your finished estimate, change one assumption by 10 times, and watch what happens. Let's say a photo is not 1 megabyte but 10. Maybe we start allowing short clips as well. Instantly, everything with size in it jumps at full step. Storage from 600 petabytes to 6000, and peak delivery from 500 gigabytes a second to 5000. But here is the part to say out loud, right? Look at what did not change. The request counts. 50,000 feed requests, 5,000 uploads, exactly the same. So, our number of app servers barely moves. One assumption blew up storage and bandwidth and left the traffic completely untouched. And that is the real payoff. It tells you which assumption is fragile. Photo size is the one you must get right because it decides storage cost, delivery cost, whether you need heavy compression, several sizes of each image, and a whole processing pipeline. Estimation does not just hand you numbers, it shows you where your design is sensitive. Now, you might be thinking, is all of this just a trick for interviews? Genuinely, no. This is how experienced engineers think before writing any code. Because at that stage, the real numbers do not exist yet. So you estimate to check, is this even feasible and what breaks first. An interviewer asking to estimate is checking exactly that. Can you make a confident call with incomplete information, which is the job? But keep it honest. An estimate decides the shape, not the details. It does not tell you the exact server count or the real cache hit ratio as well. Those come from measuring the running system and adjusting. So the rule is simple: estimate to decide the shape, measure to decide the details. And one habit that instantly sounds senior: never give a fake precise answer. Do not say 3472 requests a second. Say on the order of a few thousand, and always say the unit. Everyone in the room knows the inputs were guesses. Pretending the output is exact just shows you miss the whole point. Round and commit. So let's pull it all together. Capacity estimation is not hard math and it is not a trick. It is counting zeros and separating the workload to see the shape of a system before you build it. The whole method in one breath. Write your assumptions and their units. Round each number to one digit and a power of 10. Multiply the small front numbers and add the zeros. Split the work into real jobs because a feed request and a photo view are not the same load. Size for the busy hour peak, and most important, make every number end in a decision, right? Never leave it as a bare figure. And where the estimates stop, the exact server count you get from measuring. Do that, and the wall of numbers that used to freeze you becomes a 5-minute conversation that tells you exactly what to build. Servers here, a CDN there, object storage, background workers. You are not calculating anymore. You are counting zeros and letting the numbers end the architecture. If this made capacity estimation finally click, subscribe. That is exactly what we do here. Take the scary looking part of system design and make it simple. I'll see you in the next one.